Tonight, we are going to drift slowly outward with two small spacecraft, leaving the warmth of the inner solar system behind, and following a quiet trail toward the place where the sun's influence begins to fade. This is the story of Voyager 1 and Voyager 2, but told gently, as a long evening journey rather than a race across space. You do not need to hold every number in your mind. You can simply imagine the motion. A pale blue Earth falling away, the orbit of Mars slipping behind, Jupiter growing from a bright point into a world of storms, Saturn opening its rings like a wide, golden arch, and then, far beyond the planets, a dimmer region where the sun is still present, but softer, weaker, and increasingly distant. The Voyager spacecraft were launched in 1977, only a few weeks apart. Voyager 2 left first on August 20th, and Voyager 1 followed on September 5th. Their names are slightly misleading because Voyager 1 was called 1, not because it launched first, but because it was placed on the faster path. It would arrive at Jupiter and Saturn before its twin. At the time, the mission was expected to last only a few years. The main goal was to visit the outer planets during a rare planetary alignment, using gravity to bend the spacecraft from one world to the next. It was a kind of celestial handoff, where each giant planet gave the spacecraft a little extra speed and a new direction. The alignment that made this possible happens only about once every 176 years. Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a spacecraft could visit them in sequence, without carrying enough fuel to fly there directly. Instead, the spacecraft would borrow energy from the planets themselves. As Voyager approached a planet, it fell into that planet's gravitational field, curved around it, and left with a changed path. From the spacecraft's point of view, it was simply falling and rising. From the sun's point of view, it had gained speed. This delicate technique is called a gravity assist, and it allowed a pair of modest spacecraft to travel far beyond what their own engines could have done. Each Voyager was built in the 1970s with technology that now feels almost impossibly simple. Their computers held far less memory than a modern phone, less than a tiny digital photograph, less than the text of a short document. Their radio transmitter sent a signal weaker than many household light bulbs. And yet those faint signals could be caught by great dishes on Earth, by the deep space network, and turned back into pictures, measurements, and messages from the far places of the solar system. There is something calming about that. A quiet signal crossing billions of miles. A patient antenna on Earth listening. A spacecraft, older than many of the people who now operate it, still keeping its dish pointed home. Before Voyager, scientists already had a broad idea of what might happen near the edge of the sun's domain. The sun is not just a glowing sphere of light, it is also a source of wind. From its outer atmosphere, the corona, streams of charged particles flow outward in every direction. This flow is called the solar wind. It is made mostly of protons and electrons, a thin plasma that spreads through the solar system. Near Earth, we notice the solar wind when it interacts with our magnetic field and helps create auroras, those curtains of light near the poles. But the solar wind does not stop at Earth. It moves past Mars, past Jupiter, past Saturn, and onward into the deep. For a long time, scientists understood that this wind must eventually meet the material between the stars. Space is often described as empty, but it is not perfectly empty. The region between stars contains a thin mist of gas, dust, magnetic fields, and high-energy particles. It is far thinner than any air we can breathe, far thinner than most laboratory vacuums, but across great distances, even a faint mist can matter. The Sun, along with all its planets, is moving through this interstellar material as it orbits the center of the Milky Way. So the solar wind pushes outward, while the surrounding interstellar medium presses gently back. Where those pressures balance, a boundary forms. It is not a hard wall. There is no shell of glass, no surface that a spacecraft could touch. Instead, It is a region of changing particles and fields. Inside it, the sun shapes the environment. Outside it, the galaxy does. This great bubble of solar influence is called the heliosphere. Its outer boundary is called the heliopause. Before the Voyagers reached it, the heliopause was mostly a matter of theory. Scientists could estimate where it might be, but no spacecraft had ever crossed it directly. So, as Voyager left the bright planets behind, the mission slowly changed. It was no longer only about Jupiter's storms, Saturn's rings, or the icy moons of the outer worlds. It became a search for the solar system's quiet outer shore. Scientists wanted to know where the solar wind slowed down, where the sun's particles thinned, where galactic cosmic rays became more common, and where the magnetic field changed character. They wanted to know what it means, physically, for a spacecraft to leave the sun's protective bubble and enter interstellar space. Tonight, as we follow this story, we can think of Voyager not as a machine rushing ahead, but as a patient traveler. It moves through darkness at tens of thousands of miles per hour, and still the distances are so vast that its journey feels slow, almost meditative. Year after year it travels a little farther. Hour by hour its faint signal takes longer to return. It is a reminder that space is not scaled to human impatience. Space has its own pace, and the Voyagers, in their long silence between transmissions, have learned to move at that pace. So we begin with the simple image of two spacecraft leaving Earth, carrying instruments, cameras, magnetometers, particle detectors, and one small golden record. They were built for a planetary tour, but they became something larger. They became the first messengers from Earth to touch the edge of the sun's reach. And, softly, over the course of this hour, we will follow them there. To understand why Voyager's discoveries at the edge mattered so much, it helps to move gently through the earlier part of the journey. The Voyagers did not begin as interstellar explorers. They began as planetary visitors. Their first great destination was Jupiter, the largest planet in the solar system, a world so massive that it contains more than twice the mass of all the other planets combined. As Voyager approached Jupiter in 1979, the planet grew from a bright star-like point into a striped sphere, wrapped in bands of cloud and turning rapidly beneath its own enormous sky. Jupiter had been observed through telescopes for centuries, but Voyager brought it close. The cameras revealed the great red spot not as a simple oval, but as a complex storm system, a swirling structure large enough to hold Earth inside it. Around it were smaller storms, waves, cloud lanes, and bright zones moving at different speeds. The planet looked less like a static marble and more like a living atmosphere, restless and layered. Lightning flashed in its clouds. Its magnetic field swept through space. Its radiation belts were fierce enough to challenge the spacecraft's electronics. Jupiter was not merely a planet on a chart. It was an environment. Then came the moons. Io, the innermost of the large Galilean moons, became one of the mission's great surprises. Scientists expected a frozen, cratered world. Instead, Voyager images revealed active volcanoes. Plumes rose above the surface. Sulfur-rich material painted the moon in yellows, oranges, and reds. Io was being flexed by Jupiter's gravity, squeezed and stretched as it moved in orbit. That flexing generated heat inside the moon, enough to drive volcanic activity on a scale no one had expected. With Io, Voyager showed that a small world could be alive geologically, not because of sunlight, but because of tides. Europa, another of Jupiter's moons, offered a quieter mystery. Its surface was bright and icy, crossed by long cracks and ridges. There were fewer craters than expected, suggesting the surface had been renewed. The ice looked fractured and shifted, as if something beneath it had moved. Voyager could not prove that Europa held an ocean below its ice shell, but it gave the first hints that this might be possible. Later missions would strengthen that idea, making Europa one of the most important places in the search for life beyond Earth. In the gentle arc of the Voyager story, This matters because the spacecraft kept finding worlds that were more active, more varied, and more surprising than the old models had allowed. From Jupiter, Voyager moved to Saturn. If Jupiter was a world of storms, Saturn was a world of rings. From Earth, Saturn's rings had always seemed elegant and smooth, like a thin, shining disk. Voyager revealed that they were astonishingly complex. The rings were made of countless individual particles, from dust-sized grains to larger chunks of ice and rock, each orbiting Saturn in its own path. The rings contained waves, gaps, braids, and sharply bounded edges. Small moons helped shape some of these structures, shepherding ring particles through gravity. The system was delicate and dynamic, not a simple ornament, but a natural laboratory of motion. Saturn's moon Titan was another world that refused to be simple. It had a thick atmosphere, mostly nitrogen, with methane and other organic molecules mixed in. Voyager could not see the surface clearly because Titan was wrapped in orange haze, but even that haze was meaningful. It hinted at chemical processes happening in the atmosphere, sunlight breaking molecules apart and allowing more complex molecules to form. Titan became a place of weather, chemistry, and possibility. Later, the Cassini-Huygens mission would reveal lakes and rivers of liquid methane and ethane on its surface, but Voyager opened the door. After Saturn, the twins parted ways. Voyager 1's path carried it above the plane of the planets and onward toward the outer heliosphere. Voyager 2 continued the grand tour, visiting Uranus in 1986 and Neptune in 1989. It remains the only spacecraft ever to have visited either of those worlds. Uranus showed an unusual tilt, as though the planet were rolling around the sun on its side. Its atmosphere looked calm in visible light, yet its winds were strong. Its moons, especially Miranda, displayed strange fractured terrain, cliffs, grooves, and regions that looked as if they had been broken apart and rearranged. Neptune, farther still, was expected to be quiet and cold. Instead, Voyager 2 found a dynamic atmosphere with powerful winds and a great dark storm. Its moon Triton was even more surprising. Triton orbited backward compared with Neptune's rotation, suggesting it had been captured, perhaps from the Kuiper belt. Its surface was extremely cold, yet Voyager saw evidence of geyser-like activity, dark streaks where nitrogen gas may have carried material upward and outward. Even at the edge of the planetary realm, the solar system was not asleep. It was active in slow, strange ways. By the time Voyager 2 passed Neptune, the original planetary mission was complete. The spacecraft had changed our view of all 4 outer planets and many of their moons. They had shown volcanoes on Io, possible hidden oceans on Europa, the layered complexity of Saturn's rings, the atmospheric mystery of Titan, the strange tilt of Uranus, the winds of Neptune, and the geysers of Triton. Each world had been more detailed than expected. Each had pushed scientists to revise assumptions. And then, after all of that, the Voyagers continued. Their cameras were eventually turned off, because there were no more planets ahead to photograph and every watt of power had become precious. But other instruments remained useful. Magnetometers could still sense magnetic fields. Particle detectors could count charged particles and cosmic rays. Plasma wave instruments could listen for vibrations in the thin, charged gas around the spacecraft. The mission became quieter, less visual, more subtle. No longer were there grand images of planets filling a screen. Now there were measurements, graphs, signals, and slow changes in the invisible environment. This is where the story becomes especially suited to a calm evening. The dramatic flybys were over. The spacecraft were no longer skimming past moons or crossing ring planes. They were moving into a region no one had measured directly, where the sun's wind gradually met the galaxy. The discoveries would not arrive as colorful pictures, but as shifts in particle counts, magnetic fields, and plasma waves. They would be quiet discoveries, but profound ones. They would reveal that the solar system's edge is not a neat line, not a simple sphere, and not a still boundary. It is a changing place, breathing with the sun, shaped by the galaxy, and full of surprises. Now let us settle into the structure that Voyager was trying to cross. The heliosphere can be imagined as an invisible bubble carried by the sun through the galaxy. It is not made of glass, or ice, or rock. It is made of motion. The solar wind flows outward from the sun, and as long as that wind is strong enough to dominate the surrounding environment, the spacecraft is still inside the sun's realm. The light of the sun continues forever, fading with distance, but the solar wind does not dominate forever. Eventually, it meets the interstellar medium, the very thin material between stars. Close to the sun, the solar wind moves very quickly. It travels faster than the speed at which waves can move through the plasma. In a loose sense, it is supersonic, though in plasma the details involve magnetic fields as well as sound waves. As it expands outward, it becomes thinner, but it continues to carry the sun's magnetic field. Because the sun rotates, that magnetic field is drawn into a spiral shape, sometimes compared to water from a rotating lawn sprinkler. Far from the sun, the field does not point simply straight outward. It curves and winds as the sun turns. The first major boundary Voyager encountered was called the termination shock. This is the region where the solar wind slows abruptly from a faster flow to a slower one. It is called a shock because the change happens over a relatively narrow region and because the plasma is compressed, heated, and disturbed. Before Voyager arrived, scientists had estimates for where this might be. But estimates are not measurements. The outer solar system is enormous, and small uncertainties in pressure, density, and magnetic fields can shift a boundary by millions or even billions of miles. Voyager 1 crossed the termination shock in December 2004 at about 94 astronomical units from the Sun. 1 astronomical unit, or AU, is the average distance between Earth and the Sun, about 93 million miles. Voyager 2 crossed the same kind of boundary in August 2007, but at about 84 AU. That difference was important. The two spacecraft were traveling in different directions, and their crossings showed that the heliosphere was not perfectly symmetrical. It was not a simple round bubble centered neatly on the sun. It was shaped by the sun's motion through the galaxy, by the pressure of the interstellar medium, and by the changing activity of the sun itself. Beyond the termination shock lies the heliosheath. This is a broad, turbulent region where the solar wind has slowed, but where the material is still largely influenced by the sun. The heliosheath is a little like the foamy water near the edge of a river where a current meets an obstacle. The flow has not stopped, but it has been disturbed. The direction changes, the pressure changes, waves and turbulence appear. Voyager moved through this region for years, measuring particles and fields as it went. Scientists expected the final boundary, the heliopause, to behave in certain ways. Inside the heliopause, they expected solar particles to be common. Outside it, galactic cosmic rays should become more intense. Inside it, the magnetic field should still be shaped mainly by the sun. Outside it, the magnetic field of the local interstellar medium should dominate. The crossing might not be instant, but many expected a reasonably clear transition. Solar particles down, galactic particles up, magnetic field direction changing. Voyager 1 complicated that picture. As it approached the heliopause, it began to detect rising levels of galactic cosmic rays and falling levels of particles from the sun. That part made sense, but the changes did not happen in a simple way. In 2012, Voyager 1 passed through a region where magnetic field lines seemed to provide an unexpected pathway for particles. Some scientists called this region a magnetic highway because particles appeared able to move along the field lines more freely. Galactic particles could come inward, and solar particles could leak outward. It was not the clean boundary many models had suggested. Then, on August 25, 2012, Voyager 1 recorded a dramatic shift. Particles from the sun dropped sharply, Galactic cosmic rays rose and remained high. The spacecraft seemed to have crossed into interstellar space. But there was a puzzle. The magnetic field did not rotate as much as expected. Its direction remained surprisingly similar. For a time, scientists debated whether Voyager 1 had truly crossed the heliopause or had entered some new outer layer of the heliosphere. Later analysis, including plasma wave measurements that helped estimate the density of the surrounding medium, supported the conclusion that Voyager 1 had indeed entered interstellar space. Voyager 2 crossed the heliopause on November 5, 2018. Its experience was not identical. Voyager 2 still had a working plasma instrument at the time, allowing direct measurements of the plasma around it. That made its crossing especially valuable. It confirmed in its own direction that the heliopause could be crossed and that interstellar space began beyond it. Voyager 2 also saw a somewhat different magnetic field behavior, showing that the boundary varies from place to place. With only 2 crossings, we cannot map the whole heliosphere, but we can see enough to know it is textured, uneven, and responsive. One of the loveliest ideas in this part of the story is that the heliopause moves. It is not fixed like a painted line on a floor. The sun's activity rises and falls. Solar storms send pressure waves outward. These waves travel for years before reaching the outer heliosphere. When they arrive, they can push on the boundary, causing it to shift. The heliopause can breathe, expanding and contracting with the long rhythm of the sun. A spacecraft near the boundary might briefly find itself in one kind of environment, then another as the boundary moves past it. This means the edge of the solar system is not a place you cross in the way you cross a doorway. It is more like moving through changing weather. The wind slows, the particles change, the field becomes unfamiliar, the sun's voice grows quieter, and the galaxy's background becomes clearer. Voyager did not find a hard ending. It found a transition. It found that the solar system fades into the galaxy through a complicated, living boundary made of plasma, magnetic fields, particles, and pressure. For a calming thought, imagine that boundary now. Far beyond Neptune, far beyond the Kuiper belt, a huge invisible surface surrounds the sun. It is pressed from within by solar wind and pressed from without by interstellar material. It trembles when solar storms arrive. It is shaped by the sun's motion. It is not perfectly smooth. It is not perfectly still, and 2 small spacecraft built on Earth long ago have passed through it, sending back measurements of a shore no human eye can see. Once Voyager 1 and Voyager 2 moved beyond the heliopause, they entered a region we often call interstellar space. That phrase can sound grand and distant, as if the spacecraft had suddenly arrived among the stars. In truth, they are still very close to the sun compared with the distance to even the nearest star. They have left the heliosphere, but they have not left the sun's gravity. They have entered the local interstellar medium, the thin material that surrounds our solar system as it travels through the Milky Way. It is the first layer of the wider galaxy beyond the sun's protective wind. The first great lesson is that interstellar space is not empty. It is extraordinarily thin, but not empty. There are atoms, ions, electrons, dust grains, magnetic fields, and cosmic rays. A cubic centimeter of this space may contain far less than 1 particle on average, depending on the region and how it is measured. By earthly standards, that is almost nothing. And yet, over astronomical distances, it is enough to create pressure. It is enough to influence the shape of the heliosphere. It is enough to carry waves. It is enough to matter. Voyager 1's plasma instrument had stopped working years before its heliopause crossing, so scientists had to infer the density of the surrounding plasma in a clever way. They used the plasma wave instrument, which can detect oscillations in charged particles around the spacecraft. When a disturbance passes through the plasma, the electrons can vibrate at a frequency related to their density. By listening to these faint vibrations, scientists could estimate how many electrons were nearby. In this sense, Voyager 1 did not simply measure interstellar space, it listened to it. Those plasma wave detections helped confirm that Voyager 1 was in a denser environment than the outer heliosheath, consistent with interstellar plasma. Later, Voyager detected more such waves, some associated with disturbances from solar activity. These have sometimes been described as tsunami-like waves, not because they are water waves, but because they are broad pressure disturbances moving through a medium. A solar outburst leaves the Sun, travels outward through the heliosphere, reaches the heliopause, and then can send a wave into the interstellar plasma. Years later, Voyager can sense that wave passing by. This idea is strangely beautiful. Even beyond the heliopause, the Sun can still make itself known, not by filling the region with solar wind, but by sending disturbances that ripple outward. The Sun is quieter there, but not forgotten. Its storms can still send messages into the surrounding interstellar medium, and Voyager can still hear some of those messages in the vibrations of electrons. The second lesson concerns cosmic rays. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, moving through the galaxy at tremendous speeds. They can be produced or accelerated by powerful astrophysical events, such as supernova shocks. Inside the heliosphere, the solar wind and the Sun's magnetic field help shield the inner solar system from some of these particles. They do not block everything, but they reduce and modulate the cosmic ray flux. When Voyager crossed the heliopause, the intensity of galactic cosmic rays rose, showing that the heliosphere really does act like a kind of protective bubble. This shielding matters for Earth, for astronauts, and for any future spacecraft traveling far from the Sun. Cosmic rays can affect electronics and living tissue. They can create secondary particles when they strike matter. They can even contribute to the production of certain isotopes in planetary atmospheres. The Voyagers provide a direct measurement of the radiation environment beyond the Sun's bubble. That does not solve every challenge of interstellar travel, but it gives future mission designers a real starting point. The third lesson is magnetic. Magnetic fields in space are invisible, but charged particles feel them. They spiral along field lines. They are guided, scattered, and sometimes trapped by magnetic structures. Before Voyager crossed the heliopause, scientists expected the local interstellar magnetic field to have a noticeably different direction from the field inside the heliosphere. Voyager 1 saw a smaller change than expected. This was puzzling at first. It suggested that the Sun's field and the local interstellar field were more closely aligned in that region than models had predicted, or that the boundary was more complex than a simple transition between two field directions. Voyager 2 added a second perspective. Its crossing showed that conditions can differ in another direction. With two spacecraft, scientists gained 2 points on a vast invisible surface. 2 points are not enough to draw a full map, but they are enough to show that the map is not simple. The local interstellar magnetic field is not a perfectly uniform background. It has structure. It is part of the larger galactic environment, but it is also affected by local clouds, turbulence, and the presence of the heliosphere itself. Another important finding is that the heliopause is leakier and more layered than a simple picture suggests. Particles can cross in ways that models did not fully anticipate. Solar particles can sometimes be detected near or beyond the expected boundary. Galactic particles can enter along favored paths. The boundary is not a sealed membrane. It is more like a shifting conversation between two plasmas. Some things are held back. Some things pass through. Some things move along magnetic connections that are difficult to picture, but real enough for Voyager to measure. There is also the matter of scale. Voyager 1 crossed the heliopause at about 121 AU from the Sun. Voyager 2 crossed at about 119 AU. These distances are so large that they can feel abstract. Light from the Sun, which reaches Earth in about 8 minutes, takes many hours to reach Voyager. A command sent from Earth takes most of a day to arrive. And yet, compared with the nearest star, the Voyagers have barely begun the journey. Proxima Centauri is more than 4 light-years away. At Voyager speeds, reaching that distance would take tens of thousands of years. Interstellar space begins close in one sense, but the stars themselves remain unimaginably far. This is one of the quiet lessons of the mission. The edge of the heliosphere is not the edge of the solar system in every possible sense. It is the edge of the sun's wind, not the edge of the sun's gravity. Far beyond the heliopause may lie the Oort cloud, a distant reservoir of icy bodies that may extend a significant fraction of the way to the nearest stars. Voyager will not reach even the inner regions of that cloud for centuries. Its instruments will be silent long before then, so the spacecraft have crossed one boundary while many larger distances still remain. And perhaps that is part of why the Voyager story feels so calming. It gives us a boundary, and then reminds us that every boundary opens into something larger. The planets give way to the outer solar system. The solar wind gives way to the interstellar medium. The heliosphere gives way to the galaxy. Each edge is real, but none of them is final. Voyager crossed into interstellar space and found not emptiness, but another environment, subtle and structured, filled with faint particles, weak magnetic fields, and waves moving through the dark. The Voyagers are not starships in the science fiction sense. They are not traveling to another solar system with a destination waiting at the end. They are moving through interstellar space, but very slowly compared with the distance between stars. This difference is worth resting with for a moment. Voyager 1 is the most distant human-made object, and still, after nearly half a century of travel, it has covered only a tiny fraction of the distance to the nearest star. The spacecraft is fast by human standards, but the galaxy is larger than our instincts can easily hold. If Voyager could travel toward Proxima Centauri, the closest known star to the Sun, it would take tens of thousands of years to get there. It is not aimed that way, but the comparison helps us understand scale. A human lifetime, which feels so long from inside it, is very brief against interstellar distance. The Voyagers have traveled for decades and have only just entered the space beyond the sun's wind. They are like bottles set adrift from a small island into an ocean so wide that even the nearest shore is beyond imagination. This does not make the mission less impressive. In some ways it makes it more impressive. With a few hundred watts of power at launch, with a transmitter of modest strength, with instruments designed before the modern digital age, the Voyagers crossed the planetary region and reached the interstellar medium. They proved that a spacecraft can survive for decades in deep space. They showed that careful engineering, redundancy, simplicity, and patient operations can stretch a mission far beyond its planned lifetime. For future interstellar travel, Voyager has given us a first direct taste of the environment that must be crossed. The local interstellar medium is thin, but it contains particles. At Voyager's current speed, those particles are not a major hazard. At a much higher speed, they would become more important. A spacecraft traveling at a significant fraction of the speed of light would collide with atoms and dust grains far more energetically. Even tiny particles could damage surfaces over time. This is one reason why fast interstellar probes would need careful shielding, durable materials, and perhaps designs that minimize the area exposed to the direction of travel. Cosmic rays are another concern. Beyond the heliosphere, the shielding effect of the solar wind is reduced. High-energy particles from the galaxy become more common for robotic spacecraft. This means electronics must be protected and designed to tolerate radiation. For any future human journey beyond the heliosphere, the challenge would be much greater. Living tissue is vulnerable to high-energy radiation, and a journey lasting years or decades would require shielding far beyond what small probes carry. Voyager does not solve this problem, but it measures the environment in which the problem exists. The weak magnetic field of interstellar space may also matter for future designs. Some proposed propulsion concepts involve interacting with the interstellar medium or with magnetic fields, such as magnetic sails that could slow a spacecraft by pushing against charged particles. These ideas are still largely conceptual, but they depend on knowing the density, flow, and magnetic structure of the medium. Voyager's measurements give the first direct values from just outside our heliosphere. They are not a full map, but they are a beginning. There is another challenge that Voyager demonstrates every day: communication. As the spacecraft recede, their signals become fainter, and the time delay grows. A command from Earth takes many hours to reach them. A reply takes many hours to come back. For a probe traveling to another star, the delay would be measured in years. That means it could not be controlled in real time. It would need to navigate, diagnose problems, and make scientific decisions with a high degree of autonomy. In a quiet way, Voyager is already part of that story. Engineers send commands carefully, wait patiently, and work with a spacecraft that cannot be touched, repaired, or quickly questioned. The spacecraft also teach the importance of power. Voyager's electricity comes from radioisotope thermoelectric generators, which convert heat from decaying plutonium into electrical power. Over time, that power declines. The mission team has had to turn off instruments and heaters to keep the spacecraft operating. Each shutdown is a small farewell. Cameras went silent long ago. Other instruments have been turned off as power margins narrowed. Yet even this gradual fading has scientific dignity. The spacecraft continue to do what they can with what remains. In 2026, NASA reported the shutdown of Voyager 1's low-energy charged particles instrument to conserve power, following other power-saving decisions on both spacecraft. This is not a failure. It is the natural late stage of an extraordinarily long mission. Instruments that were expected to work for years have operated for decades. Every additional month of data from interstellar space is a gift. The next generation of interstellar-bound missions, if built, will likely be designed with these lessons in mind from the beginning. They may carry more efficient power systems, modern instruments, better shielding, and communication systems meant for even greater distances. Some mission concepts imagine reaching hundreds of astronomical units from the Sun within a human lifetime, far beyond where the Voyagers are now. Such missions could map the heliosphere more fully, sample interstellar space in new directions, and perhaps look back at the solar system from far outside. But even if no new mission leaves soon, Voyager has already created a foundation. It measured the termination shock. It crossed the heliopause. It detected the local interstellar environment. It found that the boundary is dynamic, that particles behave in surprising ways, that magnetic fields do not always turn as expected, and that the Sun's disturbances can still be felt beyond the heliosphere. These facts will remain. They will guide future questions. There is something soothing in the patience of this kind of science. It does not unfold in a single headline or a single image. It unfolds across decades. A spacecraft launched in one generation is operated by another and studied by another. Engineers who were children when Voyager launched may later become part of the team that keeps it alive. Students not yet born when Voyager crossed Jupiter may analyze its interstellar data. The mission stretches human attention across time. And so, as we think about future interstellar travel, we can let Voyager set the mood. Not hurried, not grandiose, just persistent, a slow, careful reaching outward, a willingness to send something small into a vast unknown, knowing that the answer may arrive long after the question was asked. Before the Voyagers left Earth, each was given a small symbolic cargo, a golden record. It was not needed for the spacecraft's scientific mission. It did not help navigate to Jupiter. It did not measure plasma, count particles, or detect magnetic fields. It was included for another reason, a human reason. The golden record was a message, a time capsule, a carefully chosen portrait of Earth attached to a spacecraft that might last for hundreds of millions of years. The record contains sounds from Earth, music from different cultures and eras, greetings in many languages, and images encoded in a form that could, in principle, be reconstructed. It includes natural sounds such as wind, surf, thunder, birds, and whales. It includes human sounds, the rhythms of footsteps, a heartbeat, laughter, and other signs of life. It includes music, not as a complete representation of all humanity, which would be impossible, but as a gesture, a way of saying that this planet has pattern, feeling, rhythm, memory, and art. The record also includes instructions on its cover. There are diagrams meant to explain how to play it, how to decode the images, and where Earth is located. One famous diagram uses pulsars, rotating neutron stars that send out regular pulses, as a kind of cosmic map. The idea is that the periods of those pulsars could help another intelligence locate the sun and estimate when the record was made. The chances of the record ever being found are extraordinarily small. Space is too vast, and the Voyagers are too small. But the record was never only about being found. It was also about what humanity chose to say when given the chance to speak into the dark. That makes the Golden Record one of the most tender parts of the Voyager story. It is science joined with humility. The spacecraft measure particles and fields with precision, while the record carries a broader message. We were here. We listened to waves and birds. We made music. We built tools. We looked outward. We wondered who else might be listening. Even if no one ever finds the record, the act of making it changed us because it required people to ask what Earth is, what life is, and what might be worth preserving. As the Voyagers continue outward, their scientific instruments will eventually fall silent. The power from their radioisotope generators decreases year by year. Mission engineers have stretched the available energy with remarkable care, turning off heaters, switching systems, and finding creative ways to keep communication alive. But the decline cannot be stopped forever. At some point, perhaps in the 2030s if all goes gently, the spacecraft will no longer have enough power to send a meaningful signal home. The deep space network will listen, and there will be no reply. That will be a quiet ending for the mission, but not for the spacecraft. Voyager 1 and Voyager 2 will keep moving. There is almost no friction in the space between stars. Unless they collide with something or are disturbed by gravity over immense timescales, they will continue to orbit the center of the Milky Way, dark and silent, carrying their records. They will pass near other stars only at great distances. Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445 in roughly 40,000 years. Voyager 2 will make its own distant stellar encounters. These are not arrivals in the ordinary sense. They are quiet passings through a vast galactic night. By then, Earth will have changed. Human languages will have changed. Our cities, technologies, and concerns will be different, if we are still here at all. But the Voyagers will still be themselves, small, silent artifacts from the 1970s, carrying the marks of human engineering and human imagination. Their golden records may still be readable, their instruments may be cold, their transmitters silent, but their existence will say something simple and lasting. A young species once built machines and sent them outward. The discoveries they made remain with us. They taught us that the outer planets were more active and varied than expected. They revealed volcanic Io and mysterious Europa, complex Saturnian rings and hazy Titan, tilted Uranus and stormy Neptune, geysering Triton, and the deep structures of the heliosphere. They showed that the solar system's edge is farther and more dynamic than simple models suggested. They found that the heliopause is not a clean wall, but a shifting boundary. They measured interstellar plasma directly. They showed that the sun's storms can send waves beyond its own wind. They gave us real data from a region that had once been only theoretical. Perhaps the deeper lesson is that exploration changes the meaning of the familiar. Before Voyager, the solar system was already our home. After Voyager, it became richer, stranger, and more alive. The boundary of the sun's influence, once an abstract idea, became a measured place. The interstellar medium, once only observed from afar, became something a human-made spacecraft could touch. The Earth, seen from Voyager's distance in the famous pale blue dot image, became at once smaller and more precious. So tonight, as the story comes to rest, we can picture the scene gently. The sun is far behind, still the brightest star in Voyager's sky, but no longer surrounding the spacecraft with a strong solar wind. The planets are invisible from that distance, tiny points lost in glare and darkness. Around the spacecraft is the local interstellar medium, thin and quiet, threaded by magnetic fields and crossed now and then by waves. Somewhere behind it, Earth turns slowly, blue and white, alive with oceans, clouds, forests, cities, and sleeping people. Voyager continues. It does not hurry, though it moves very fast. It does not know that it has made history. It simply follows the path given to it, keeping its antenna toward home while it can, carrying its instruments and its record, crossing distances that human minds can only approach through metaphor. A shoreline, a bubble, a breath, a message in a bottle. And that is where we can leave it for now. Two small spacecraft drifting beyond the sun's wind into the soft darkness between stars. They remind us that science can be precise and still feel gentle. It can measure magnetic fields and still awaken wonder. It can count particles in the dark and still tell a story about home. The Voyagers have shown us that the edge of the solar system is not an ending. It is a threshold. Beyond it is not emptiness, but another quiet layer of the universe, waiting patiently to be understood.